Welcome back, boys and girls, to the second part of this lecture. We're going to do example 4 now on page 580. And of course, as you can see, what is new and interesting about this particular example is that we have an infinite upper and an infinite lower endpoint of integration. We're going to have to divide this into two improper integrals, one where we're going from negative infinity to, let's pick a point, it kind of doesn't matter, we'll choose 0 as a convenient point, to 0, and then plus the integral from 0 to positive infinity. Both of these of our function, I'll just call this f of x right now, dx. Both of these are improper integrals, but this is the way we have to handle the situation when both endpoints of integration are infinite. Now for each improper integral, we're going to have a limit attached to it. So let's start with this first improper integral, which is going to be the limit, and we'll use a, it doesn't really matter what letter you use, as a approaches negative infinity from a to 0 of our function. Sorry, I'm getting a little bit of a cold, I think. And then plus the limit, as we'll let this be our b. b approaches positive infinity from 0 to b of our integral. So again, it's kind of like two of the previous examples for the price of one. Now we do need to integrate here, and I think I'll just kind of stay up here and do the integration. What you discover is that this is going to be an arctan integral. If you think of u as being e to the 2x power, nope, sorry, let me back up a little bit, e to the x, then u squared is e to the 2x. And of course du is e to the x. So this is really du over 1 plus u squared. Just ignore that sound. That's actually my fax machine. Du over 1 plus u squared, which of course is arctan. But since u is equal to e to the x, it's going to be arctan of e to the x. Now, with that in mind, let's go ahead and evaluate our limits. We have the limit as a approaches negative infinity, arctan e to the x from a to 0, plus the limit as b approaches infinity of arctan e to the x from 0 to b. When we plug in 0 and a, remember we're not going to take the limits yet. We're just going to say limit as a approaches negative infinity of, now we're going to have arctan e to the 0 minus arctan e to the a, and then of course plus the limit as b approaches infinity of arctan e to the b minus arctan of e to the 0. Now it turns out that of course e to the 0 is 1. Arctan of 1 would be saying the tangent of what angle is equal to 1, and that turns out to be pi over 4. So this value is pi over 4, and this value is pi over 4 over here. That's right. Okay, wait, did I do this correctly? You're going to have pi over 4, and then, we'll see. Now, I'm going to go ahead and plug in negative infinity in for a. This is going to give me pi over 4 minus arctan of e to the negative infinity, plus, and if I plug infinity in for b, I'm going to end up with arctan of e to the infinity minus pi over 4. Sorry, I had to do a little coughing off of the audio. Now to finish this off, we're wondering, since e to the negative infinity is really 1 over e to the infinity, since I'm running out of room, which is really 0, we're taking the arctan of 0. And we remember once again, where is tangent equal to 0? At 0. So let me change colors and go up here. I have pi over 4 minus 0, because this becomes arctan of 0. Then arctan of e to the infinity is really arctan of infinity. Well, we're wondering once again, tangent of what angle gives us infinity? Turns out that's pi over 2. And then of course we have minus pi over 4. These guys go away, as does minus n. Look what emerges as your answer, pi over 2. The area from negative infinity to positive infinity under this curve is pi over 2. That kind of blows my mind. Now let's go to the second type of improper integral, where we have infinite discontinuities within the function on the interval. And so that's going to be at or between the limits of integration. So it doesn't necessarily have to be within the endpoints of integration. It could be one of the endpoints of integration. So notice it says if f is continuous on the interval and has an infinite discontinuity at b, or at a, at either one of the endpoints, then you again have to set up a limit as the value is approaching that infinite discontinuity. And of course, you can also have an infinite discontinuity somewhere on the interval. You would have to divide it into two improper integrals. Once again, it turns out in the first two cases, the improper integral converges if the limit exists. Otherwise, the improper integral diverges. So if this limit exists, then you have a convergent function. In the third case, the improper integral on the left diverges if either one of these guys diverges. And of course, if they don't diverge, then you have a convergent integral. So that's kind of the same as before. Let's do a couple of examples. Here we have an improper integral with an infinite discontinuity. Now we see, because we can look at this function and recognize that there's an infinite discontinuity at 0. So we're going to say, no, let's say the limit as b approaches 0, and again, in this case, positively, because we can't just be approaching 0 from the left and the right. This is an asymptote after all, and there shall we not pass. So this is now going to become the limit as b approaches 0 positively from b to 1 of x to the negative 1/3 dx. Integrating this gives us, let's see, 2/3, which is 3/2, x to the 2/3 from b to 1. This will be 3/2 minus 3/2 b to the 2/3. Now let's take our limit. As you can see, I am going to be able to plug 0 in here, and it's just going to give me 3/2 as the answer. It's a little bit easier perhaps than the other kind of improper integral. Now let's look at one that diverges. Here we see a function once again with an asymptote at 0, so this little fellow is an infinite discontinuity. We're going to switch him out and take the limit as b approaches 0 again positively, because you can't cross the asymptote, and since the interval is from 0 to 2, we're just going to get as close to 0 as we can from the positive direction. And then that's going to be from 0 to 2, and we have x to the negative 3 dx. When we take that integral, we end up with negative x to the negative 2, which is negative 1 over x squared, from b to 2. And I'm just holding off on the limit for a moment. This becomes negative 1 over 4 when you take 2 squared, and then minus a negative, which becomes plus 1 over b squared. Now, when you take the limit of this function, limit as b approaches 0, and you plug 0 in here, big problem. That's not going to happen. So we find that this is a divergent integral, and we are not going to be able to calculate a value for the definite integral. Okay, let's do a couple more. We're almost done. Example 8 on page 582, an improper integral with an interior discontinuity hidden within this little function is an asymptote at 0. And so we're going to have to divide this into two different integrals. We're going to say, since 0 is the problem area, we're going to call this from negative 1 to 0 of dx over x cubed, plus the integral from 0 to 2 of dx over x cubed. And each of these is going to require a limit. 0 is the discontinuity, so we're going to say the limit, we'll say as b approaches 0, in this case negatively, because we're going from negative 1 and we're approaching the asymptote very gingerly from the left direction, negatively of this integral from negative 1 to b, and we'll just say this is x to the negative 3 dx, plus, and then we're going to let a represent our problem area here, the limit as a approaches 0 positively of the integral from a to 2 x to the negative 3 dx. Now you can integrate this and plug in numbers, but since we saw in our last example that this diverged, we know that we're going to get that the entire integral here diverges. So I'm not going to go any further, only because we found in the previous result that this piece diverges, and remember what it said, if either of the improper integrals diverges, then the entire integral diverges. Now notice down here, remember to check for infinite discontinuities at interior points as well as endpoints when determining whether an integral is improper. If you had not recognized that the integral in example 8 was improper, you would have obtained the incorrect result. You would have integrated, you would have plugged in 2, -1, you would have got a value and thought, oh, look at me, I got 3/8 as my answer. It's completely wrong. It is up to you, mathematician, to recognize, hold it, wait a minute. There is an asymptote in here between -1 and 2, therefore I have to set up my 2 improper integrals and evaluate the limits. That's your job. All right, last example. This integral is improper for 2 reasons. One limit of integration is infinite, and the integrand has an infinite discontinuity at the outer limit of integration. So here, as you can see, approaching 0 from the right direction, we have a problem because there's going to be an asymptote there. That's this fellow. And of course now we have, as the upper endpoint of integration, we do have an infinite infinity, which cannot be done. So we're going to have to be very careful about evaluating this improper integral as well. I'm going to pause for 1 second. Sorry, back again, boys and girls. I am having a little trouble coughing, and I just hate to do it in front of you like this. Now, what we're going to do is divide this up into 2 integrals. We're going to pick some convenient region or a convenient number between 0 and positive infinity. We'll just pick 1. How's that? And we'll divide this up into the integral from 0 to 1 of our function, dx, plus from 1 to positive infinity. Well, obviously both of these are improper integrals and will require limits. And so we will say then, since 0 is a problem, we'll say the limit as b approaches 0 of our function from b to 1. Right now I'm just kind of shorthanding it instead of rewriting it over and over again, plus the limit, and we'll say a to infinity. Kind of doesn't matter which letter you do, so don't be confused by the fact that I let this be b instead of a, this be a instead of whatever. And then we're going to go from 1 to a, f of x dx. Now, integrating this is going to require a little u du substitution. If I let u equal the square root of x, u squared is x. Oh, this is interesting. And then dx is going to be 2u. So if I rewrite the integral using u's, this is what I get. 2u, well, actually dx is 2u du. 2u du over u, and then u squared plus 1. And as you can see, the u's cancel, giving me 2, let's put the 2 on the outside, du over u squared plus 1. There's our old friend arctan again. So this integral is going to be the arctan of u, which is the square root of x. So, changing color again, we're going to take the limit as b approaches 0 of the arctan of the square root of x from b to 1 plus the limit as a approaches infinity of the arctan square root of x from 1 to a. Now plugging in 1 gives us arctan of 1 minus arctan of square root of b, and then over here we're going to have plus arctan square root of a minus arctan of 1. Now you can see these arctan of 1s are going to both go away, right? So we don't need to worry about those. And now let's plug in the values that we have. Negative arctan of 0 plus arctan of infinity, right? Back again, boys and girls, and I just noticed a little error that I made. Remember that this was 2 arctan of u. And so this should have been 2 here and 2 there, which makes basically all of this times 2, which is ultimately going to make all of this 2. What is arctan of 0? Again, the question is tangent of what equals 0? We know that that's going to be 0. Tangent of what equals infinity is pi over 2. So this is going to be 2 times pi over 2, which is pi, our old friend pi. And isn't it fitting that we end on that note? The area under the curve from 0 to positive infinity of this function is pi on the day after Pi Day. And here's your homework page. 574, 1 through 4 all, 6 through 48 multiples of 3, and yet another pi joke. That's it.